Let's now put it all together and see how all of these different electrical components can be used to make our robot go at a precise speed. So let's first start by overviewing the different components we have to our system. We have our microcontroller, the ESP32S3. We have our motor driver, the DRV8835. We have our micro gear motor. The gear motor here, the gear part of gear motor just signifies that there's a gearing system here to take the speed of the axle, gear it down, increase the torque, and have an output shaft that's slower but much stronger, so we can actually have it drive a wheel. And we have our encoders, using a quadrature encoder mechanism. Let's fill in the blanks for these different components. So the microcontroller is connected to the motor driver, and it has two pins connected. The enable pin, which is controlling the speed using a PWM signal, and the phase, which is controlling the direction using a GPIO signal, general purpose input-output signal. The motor driver is connected to two parts on the DC motor, the out 2 and out 1. So let's label those so that we don't forget that this signal is denoted as having two different cables connected on that one red line. Same thing here. And technically there are more things connected to the microcontroller. I'm just going to worry about the data signals and less about the power signals for this diagram. It's cluttered enough as it is. Interestingly, the encoder is not actually physically connected to the DC motor, it's just around it and measuring, well, I guess that assumes that I'm not considering the magnet part of the encoder, which I suppose it is. So the magnet on the back of the axle, back here, is directly connected to the motor, but the Hall effect sensors and the circuitry used to measure the readings from the Hall effect sensors aren't directly connected to the motor. But those two signals, that would be A and B, are both GPIO signals. And I guess it's worth noting that out, and now I'm realizing I said out 2 and out 2, both of those we would call power signals. We're basically turning on and off power. And I guess more specifically, I could also denote that those are done using a PWM. So the units here would be in volts, and the output shaft rotation, which I'll denote with alpha, would be in radians per second. A and B are measurements, and they just are really giving us pulses. So no real units there. Same on the signal shown here, no real units to speak of. This system diagram is at a fairly high level, and it's not necessarily what you would find a control engineer using. Instead, what you might find a control engineer using is this more general purpose diagram on the bottom. So instead of calling it a robot or worrying about the fact that there's a microcontroller and a motor driver and also a DC motor, we're really just going to wrap all of those components together and call that the system. Our controller, which we think of as running on the microcontroller, a control engineer is just going to write that sort of algorithmically as a separate block. So you can think of this as an algorithm, and this as like the physical system. Sometimes it's called the plant. And I believe that terminology just comes from a lot of control systems being used in industrial plants when this field was first being innovated or invented. And generically, we're going to call this a sensor now instead of specifying the fact that it's an encoder type sensor. Well, now that we have this more generic diagram, let me fill in what you might find in a control engineering textbook or a chapter of a robotics textbook on control. We have R, and that's a lot of times called the set point. it's user specified, or if it's an autonomous system, then it's software specified. But it's what speed, in our case for the robot, it's what speed we want the robot to go. Let's assume for now it's just going straight forward, so it's just a single velocity number. Later on, we'll control things like both the orientation, the angular rate, and the forward velocity. So angular and linear velocity. The other signal coming into this block here is actually the current measured output. And I'm going to draw that as y with a hat on top of it. The hat is just to denote that it's a sort of estimate of the actual output of the system. So if we remember the diagram I drew on the previous slide, our output I was calling alpha, and that was the angular rate of the motor. In most places you'll see the output of a system denoted as y, and the measured version of it as y hat, just to denote that there's probably some sort of variance between the two, some sort of disturbance between the two. A discrepancy that it's useful to remember, because sometimes we don't sometimes we don't care how far off this number is. Sometimes it's really important, so we can build in safety margins to know how inaccurate our sensors might be. Later in the semester, we'll start talking about filtering, things like particle filters and Kalman filters, and we can actually precisely say what we expect the variance on our measured variable to be. This line here, coming out of that summing circle, is E. And E is the error between those two signals. So this little summing block here is really just saying that E is equal to R minus Y hat. And it's useful to do design almost all of our control systems based on the error of what the user specified the output should be and the actual output as seen through some sort of sensor. For historical reasons that I'm not quite aware of, the controller's output is usually denoted with U. And one last hidden line that is sometimes useful to remember, sometimes it's unnecessary, is that the system itself has some form of disturbances interjected into it. Those can come from the environment. Something like dirt on the ground or large rocks or something that people have brought in from outside are going to throw off how fast our wheels are spinning just because our robots are so small. Those disturbances can also be sort of intrinsic. I would call the environmental disturbances extrinsic, and they can also be intrinsic, such as the motor overheating. And maybe its behaviors, its dynamic, is a little less well modeled by whatever we expect to be in this block once it gets hotter. For example, the voltage might be, you might need to increase the voltage even more to get the same output when the motor is starting to get too hot. Actually, the battery is another good example of an intrinsic difference in the system itself. As you use the battery, its capacity starts to go down a little bit. Not its fully charged capacity, but when you fully charge it, the motor will be at about 4.2 volts. As you use some of its capacity due to the chemistry on the inside of the battery, it'll actually only be able to give you a potential difference, a voltage across the two terminals closer to, 3.4 or 3.5 before we want to change it out for a new battery. We're mostly going to ignore disturbances and the fact that this is Y hat instead of Y. We're going to ignore that for the purposes of this lecture. It'll come into play later on in the semester, though. The first type of control pattern we're going to look at is really the simplest type of control that you can have. Essentially, we're going to say that U is just equal to Kp times E. And before I fill in this chart, it's worth pausing the video and seeing if you can remember all the different labels for the different signals. Let's expand our equation here for U just a little bit as a reminder that the control output is going to be a function of what the user has specified as the velocity, so I don't know, 20 centimeters per second, and the current velocity as measured by the encoders. Maybe we're only going 19 centimeters per second currently. Let's fill in the dimensions of each of these units. So like I said, these would be in meters per second. I just said 20 centimeters per second, but let's just stick to the standard units, meters per second. The measured velocity would also be in meters per second. So, this is called has a fancy term of dimensional analysis. We're just going to make sure that we can understand what all of our different terms really mean. Sometimes that's helpful, sometimes it's a little bit confusing because, like for example here, what we really want as the output is some radians per second, for example. Or really what we care about more is what's a value that we can output from our motor driver to achieve a certain radians per second. So for example, going back to our original diagram here, it's not clear if U should be the value here or if U should be the value here. So let's explore some of those possibilities. And the easiest way to do so is by just seeing what happens and what do we want to happen for different values of the signals that appear on our chart. So that's what this table is going to give us. For some of the values in this table, I'm going to give us really concrete numbers. So for example, maybe R, the user has set it to 0.2. And in this case, we would say that's 0.2 meters per second. And let's say we're currently going 0.18. Let's have another example where we're going too fast. And finally, let's have an example where we're already going the speed that we want to be going. What we're going to do now is just look at the remaining values here and try to figure out what we would like them to look at, or what we would like them to be. So I'll draw a little line here to denote that these are current values, and these are, let's say, updates. We can call them outputs, and in some cases, next values. They're things that we're doing in the current time step, not just measuring things as they were in the previous time step or at the end of the previous time step. So let's start with E. Since E is just R minus Y, it has the same units, meters per second. And in this case, I'm not going to worry too much about the exact value, but here I'm just going to denote that it's a positive value, and that's because R is greater than Y hat. Likewise, I'm going to say that here is a negative value, and when the two, when our set point and our measured value are the same, the error is 0. Okay, so under those circumstances, let's focus in tightly here on Y. What do we want to happen? What do we want to happen to the motor? Well, in the case that we are going too slow, our requested speed is 0.2, but we're only going 0.18. We really want to increase our speed. So in this case, we would say increase. And to increase our speed, we need to increase our PWM duty cycle. I'll write that as a reminder here, duty cycle, with the units of percent. And let's fill in the two rows beneath that one. So what do we want to do when we're going too fast? We want to go 0.2, but we're going 0.22. That means we want to decrease our value for Y. We want to decrease how fast the axle is spinning. And to do that, we know that we need to decrease the voltage applied across the motor terminals. And by decrease the voltage across the motor terminals, I'm referring all the way back to this equation here, which is the effective voltage across the motor terminals. The motor will always receive the 3.7 volts, but the average, based on the duty cycle, is how we reduce the voltage. Finally, what do we do if we're going the correct speed? Well, in that case, we want Y to stay the same, which means we want the PWM value to stay the same. The last thing we need to do now is figure out how we want to handle U in these different cases. And U is a little tricky. Some people might have the gut reaction that U and PWM are really the same thing, meaning we want to just have U in the range 0 to 100%, and that's the only thing we need to worry about. On the other hand, PWM is not how we handle the direction of the motor. So another example we could have here in our table is what happens if we're going 0.1, if we request going 0.1, but we're currently going in reverse, so we're going in the negative direction. We don't really have any way to specify that here in our table with PWM as a percentage. Instead, we'll handle that with U, and we'll just look at the value for U and see if it's negative. That means we want to change the dir connection. So we'll have two connections here, the dir, the direction, and the speed, which is a PWM signal. So we're essentially going to have U do double duty here, and we'll just convert it to a PWM signal. And if it's a negative value, we will convert it to a direction signal that way. So with that being said, one control scheme that works pretty well is that if we don't want to make any changes, meaning that we're going the correct speed already, we just leave U to 0, which works well with the equation that we had before, which is that U is equal to Kp times E. So in this case, E is 0, which means U is 0. So no special handling needs to happen under that circumstance. What happens if we are going too slow? So the first row. Well, in that case, we want U to be a positive value because we need it to be an increase to our PWM. And the final case is what happens when when our speed is too fast. Well, we need U to be a negative value so that we decrease our PWM signal. And that all works well with the equation as we have it up here. Let's fill in one example. Let's say that we're currently wanting the robot to go in reverse, negative 0.3 centimeters per second. And it's currently going negative 0.2 centimeters per second. If you take R minus Y, you'll get a difference of negative 0.1 centimeters per second, which means U is going to be Kp times negative 0.1 centimeters per second. We will decode that into two values. So that means our dir needs to be 0 to denote negative direction, the reverse direction, and our speed is going to have to be whatever the value is from that part of the equation, the absolute value of this essentially, converted into a PWM percentage. And that's a parameter that you'll tune. This Kp, it's something that you will find a good value for. If it's too high, you'll find that your robot's behavior is too jerky. If it's too slow, it means it reacts too slowly, and it takes way too long to get up to the speed you want it to be. The last thing I'm going to comment on, and I'll use some space here at the bottom of the slide, is that there are some important sort of practical considerations that don't show up when you just look at the control theory version of this equation. And that's that, your PWM value that you set. So let's say that PWM is something that we want to map from U in its range. So let's say min U to max U into the range of min PWM, and max PWM. We want to map from one range to the other. The minimum PWM value is 0 and 100, and the values we have for the minimum U and maximum U are other parameters that you'll have to configure. So something else to take into account. One final thing is that the values for U, you'll also want to make sure that U is bounded in some degree. If you look at this equation up here, depending on the value of E and the value for Kp, you might see that your value of Kp is way too large. Under some circumstances, for example, if you have a huge change in velocity that you're requesting, let's say you were asking it to go forward at 0.4 centimeters per second, and then to get to the next goal, let's say we're going from waypoint to waypoint. To go to the next goal, you need it to go in reverse 0.4 centimeters per second. That means your error is going to be really large, and regardless of the value of Kp, your value of U is going to be really large. So often, with this type of control scheme, you'll also need to constrain your value of U between some min and some max. And I'm sorry for this getting so clustered. But in the next chapter, we'll actually go through what this looks like to code up.